Hello again, all. This is the Penncrest High School AP Physics C video series, and this is video 5A, Rotational Kinematics. So up until this point, we have studied four major content areas of mechanics, kinematics in 1 and 2 and 3D, Newton's laws of motion, work and energy, and then center of mass or impulse and momentum. Each of these major content areas has a rotational or angular analogy. We're going to look at kinematics of rotation, Newton's laws for rotation, work and energy, and also angular momentum. So we're going to begin with rotational kinematics. We know that kinematics is the study of motion. Obviously, rotational kinematics is going to look at the kinematics of objects that are spinning or rotating. The good news here is that the concepts of position, displacement, velocity, and acceleration are virtually identical, with one critical difference. Instead of measuring distances with meters as we did in a linear sense, rotational kinematics measures position or displacement with angular measurements. The preferred method to measure angular displacement or position is the radian measure. So, as you're probably aware, 360 degrees of displacement would be comparable to 2 pi radians in the radian measure. In that sense, 1 radian is about 57.3 degrees, which is actually a pretty large measurement in a relative sense. We will use radians to indicate angular position or displacement, and as we move through the progression of kinematics variables, we will see radians anywhere where we would have seen meters before. There is a standard sign convention for rotational motion in the event that the object in question is spinning in the plane of the page or in the plane of the screen. We would say that counterclockwise rotation is considered positive, and clockwise rotation is considered negative. Again, these are standard sign conventions. That means they're used conventionally. They don't have to be used all the time, and we are free to alter the sign convention if it suits our needs, as we will see, most notably in this section on torque and Newton's laws. So one way that you can remember this is another version of the right-hand rule. If you curl the fingers on your right hand so that your fingertips point in the direction of the rotation, your thumb will point in the conventional direction that's used to describe the vector. So if our screen was a standard XY plane and we had a Z direction where the positive Z direction was extending out of the screen at us, which is the standard 3D sign convention, your counterclockwise or positive rotation would be described as having a direction along the direction of your thumb, which is out of the screen or out of the page. So in a standard XY plane, if the object is spinning counterclockwise, we would say that its angular velocity, for example, would be in the positive Z direction or in the K direction. Likewise, if the object is moving clockwise in the XY plane, we would curl our fingers sort of down and to the right there, and our thumb would point into the screen, meaning it would have a negative Z direction or negative K. This would apply to any of the kinematics variables that you associate with being vectors. So position or displacement, angular velocity, angular acceleration. these all have directions that would be determined in the same manner. Okay, so for example, we have a disk here that is rotating in the XY plane. We have sort of changed the orientation here. You can see how the axes are arranged. Notice and remember that the positive directions for each one of these axes directions, the positive directions are indicated by where the label is located. So Z, positive Z is to the left, positive Y is up, and positive X would be sort of coming out of the screen at you. This disk is oriented in the XY plane, and if you're looking at it from along the positive Z axis, so you're located somewhere on the left, this object is rotating counterclockwise. So when we consider which direction omega points, again, you want to curl your fingers so that they are pointing sort of into the screen or into the page, and you'll notice that your thumb is pointing to your left. So that would indicate that the angular velocity in this case would be pointing along the positive z-axis, and if we were reporting the answer in standard IJK notation, it would have a positive k unit vector associated with it. Okay, so we also need to consider the translations into linear motions of the points along the outer edge of this disk. We have 4 points labeled here, A, B, C, and D, and these relationships, the linear velocity of any point along this, or any point on this rotating object, the linear velocity v, is related to omega through omega times r. R is the distance from the rotation axis to where that point is located. A sub t, what we call the tangential acceleration, is related in the sense that it equals alpha times r. Alpha, of course, is the angular or rotational acceleration. And then A sub c, the centripetal acceleration, again, is equal to v squared over r. It is also equal to omega squared times r. You'll notice that we have an apparent unit discrepancy here. V we want in meters per second, and our omega term is in radians per second. That's the good thing about radians, because they're really just a ratio. The radian unit measure kind of goes away when we want it to, and it comes back when we need it to. So these quantities, v and acceleration, will give you the units that you want: meters per second in the case of velocity, meters per second squared in the case of acceleration. Note that A sub t is sort of tangent to that particular point's circular path as the object rotates. A sub c, centripetal acceleration, is going to be towards the center, wherever the point happens to be located at a particular time. So if we were to consider point A, and that this object is rotating as shown in the xy plane with some alpha term, some angular acceleration that is making it speed up. If we consider point A and its linear velocity, again, that's going to be tangent to point A's path. When point A is at the location shown, its linear velocity is going to point more or less into the screen along the negative x direction. Likewise, its tangential acceleration is in the same direction as v because it's speeding up. And its centripetal acceleration, A sub c, is going to point towards the center, which is down, and in this case, in the negative y direction. So you can see that this will lend itself well to multiple choice style questions. I have a number of these types of images with the disk oriented in all different planes and rotating in different directions. So you will certainly see this again. Okay. Now, formulaically or mathematically, rotational kinematics works in the same way as linear or straight line kinematics. You'll recognize the formulas on the left side of the screen in the red box. These are the linear kinematics formulas that are associated with constant acceleration. On the right are the rotational analogies. These formulas are effectively the same. You can see the transference, the position x in linear motion is represented in rotational motion using a theta. Theta sub naught or theta sub 0 is obviously the initial angular position. Omega sub naught is the initial angular velocity, and then alpha is the angular acceleration. For some reason, the third formula here, omega squared equals omega naught squared plus 2 alpha theta minus theta naught, that one for some reason is not included on the formula sheet, but it is a good one to know. It's definitely a useful formula. If you know the analogies for position, velocity, and acceleration, it should be easy to generate that formula using the linear one, which is on the formula sheet. Make a note, please, that you are only allowed to use these formulas when the angular acceleration is constant. Okay? So these are the formulas that are associated with constant acceleration, and you can't use them in the event that there is an angular acceleration alpha that is a function of time. Okay? So the same progression in the event that we do not have constant angular acceleration, the same progression applies to rotational kinematics that applied in linear kinematics. When we go down this progression from angular position to angular velocity to angular acceleration, as we go down the progression, we use the derivative. And if you remember, this is when the polynomial degree decreases. So if our position is a function of t cubed, when we do the angular velocity and we take the derivative, the degree of the polynomial should decrease from 3 to 2. And then when we do the derivative again to find the acceleration, the degree of the polynomial would decrease again to a linear term. If we are going up the progression, if we have a function for the angular acceleration that is a function of time, when we go up the progression to find the angular velocity, we take the integral of the acceleration function. If we then go up to position or displacement, we would take another integral of the angular velocity term. So make a note that in the event that you're given a position function that has a polynomial degree greater than 2, you have to use calculus. If you're given an angular velocity function that has a degree that is greater than 1 in terms of t, then you have to use calculus. Okay, otherwise you're allowed to use the formulas for constant acceleration. Okay, so that's it for rotational kinematics. Again, it's pretty straightforward. And next up is Newton's laws and torque. So until then, enjoy, and I'll see you again soon.